So now we're going to develop, also in 11.1, example 3, the Taylor polynomials for e to the x. They want orders of 0, 1, 2, and 3. Okay, so the first thing I'm going to do is I'm going to start writing out my derivatives. So I'm going to have f of x equals e to the x. Oh, and we are centered at x equals 0, which makes it easy. So at 0, I get e to the 0 is 1. The first derivative would be e to the x at 0 is 1. Okay, and I've already decided there's no sense in doing any more of these. Every single derivative at 0 is going to be 1. Okay, so they want p sub 0. P sub 0 is just going to be the very first thing, the f of x, so it's 1. P sub 1 is going to be the 1 plus the 1x over 1 factorial. So I've used this one and this one to get those. P2 goes all the way out to the second derivative, so I have the 1 and I have the x. The next term is a 1, x squared over 2 factorial. The third one, 1 plus x squared over 2 factorial plus 1x cubed over 3 factorial. So I have all my terms, and it says graph f and the polynomial, so they want you to go in your calculator, graph e to the x, and also graph all 4 of these, and notice that they get closer and closer to being accurate. The one thing that they did do here, and they didn't even say they were going to do it, is you need to be able to come up with p sub n of x. So you would write 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 out to x to the n over n factorial. Now, what does that summation look like? Well, we started at 0, and we would be plugging in x to the k over k factorial. That's what's generating it. When k is 0, you get x to the 0 over 0 factorial. That's 1. When k is 1, you get x over 1. That's the x. When k is 2, you'd get x squared over 2 factorial. So as you plug them in, when you plug in 0, you get 1. When you plug in 1, you get x, and so on. So the goal is to be able to write it as a summation. This was part A, getting all of these. Part B wants us to use the polynomials to approximate e to the 0.1 and e to the negative 0.25. It says find absolute errors, meaning take the actual function and subtract your approximation. Use calculator values for the exact values of f. Okay. So if you go to your calculator and you do e to the 1, you get 1.1051709. And the calculator value for this one is 0.77880078. Now we are supposed to go through 0, 1, 2, and 3. So we're going to make a little chart here. We're going to say n, and we have to 0, 1, 2, and 3. We need our approximation for, let's be the 0.1. Then we need the absolute error for that. Then we need the approximation for negative 0.25 and the absolute error for that. Okay, so when n was 0, we had the function was p of 0 is 1. So no matter what you stick in, you get a 1. The absolute error is going to be e. Oh, let me write it above it. Silly, not going to fit. E to the 0.1 absolute value minus the polynomial at 0.1, whichever polynomial we're at. So you take your calculator and you do e to the 0.1, that's that 1.1051709, and subtract your first summation, which was 1, and you get 0.1051709. 105 if I round to 3 places. If I put negative 0.25 in, again, I still get 1. And so here I get 0.221 for my error when I subtract it. When p is 1, or when n is 1, I'm plugging in 0.1, and I'm going to go up here, plug in 0.1 right there. So 1 plus 0.1 is 1.1. I'll keep going down here. When n is 2, I would have the second one right there. So 1 plus 0.1 plus 0.1 squared over 2 factorial. And your calculator should give you that. When you do 3, the third polynomial, this guy right here, and you plug in 0.1, you should get 1.105167. Now you take each of these and subtract them from your e to the 0.1 that you calculated on your calculator. Subtract the 2 and write the absolute value. And this one is 0.00517. This one's 0.000171. And this one's 0.0000425. And they wrote them in scientific notation in the book, but I want you to see how tiny the error is. Over here, doing the same thing, only plugging in a negative 0.25, you get these answers. And when you subtract them from the actual answer for e to the negative 0.25, your errors are even tinier. Here you get 0.0288, and then the next one is 0.00245, and then 0.000155. So you see, just taking the polynomial out to the third degree, 4 terms, your error is very tiny. So for things close to 0, because remember we were doing this centered at 0, and 0.1 is close to 0, it's pretty accurate. Now we're going to go on to example 4. It says use polynomials of orders n equals 0, 1, 2, and 3 to approximate the square root of 18. Okay, so the function I would have to use would be the square root of x function. Now, since I'm having to go out to 18, I'm thinking I want to center this at 16 because I know the square root of 16. So 16 is the closest perfect square to 18. So I'm going to plug in 16, and I get 4. The first derivative is going to be 1/2 x to the negative 1/2. At 16 is going to be 1 over 2 the square root of 16, so that's going to be 1/8. The second derivative is going to be negative 1/4 x to the negative 3/2. Sticking in 16, you get negative 1 over 4 the square root of 16 cubed, and you end up with negative 1 over 256. And if we go to a third one, now we get 3/8 x to the negative 5/2 evaluated at 16. Oops, not negative 1. This is going to be negative. This is going to be 3. 8, the square root of 16 to the 5th. And according to my calculator, I get 8,192 down here. So I need to find all the polynomials. So what I'm going to do is I'm going to write out p sub 3, and then I'm just going to use the appropriate pieces as I go. So p sub 3 is going to be the function evaluated at 16, which was 4, the derivative, which was 1/8 x to the 1 over 1 factorial, the second derivative, which is negative 1 over 256. Oh, it's not just x, though. It's got to be x minus 16, because I centered at 16 and not at 0. And this is 2 factorial. And then the third derivative, 3 over 8192, x minus 16 to the third over 3 factorial. So if I'm looking at this in pieces, just this piece is p sub 0. This much is p sub 1. All the way to here is p sub 2, and the whole thing is p sub 3. So now they wanted us to approximate the square root of 18. Okay, so we make a chart again. You'd go through and stick in all your answers. You're sticking in an 18. You need the actual square root of 18 off your calculator. Oh, do they want us to do that? Yeah, they want us to use the calculator version. Okay, so we're going to go through and say when n is 0, 1, 2, and 3, I need p sub n of 18. Oh, I can't write that high. Let me go over here. N is 0, 1, 2, and 3. I need the approximations at 18, and then I need the absolute error, which in this case is going to be the square root of 18 minus whichever p I'm currently on. So when I stick in on the 0 term I'm looking at it, the answers are just 4. When I stick 1 into the first two terms, I get 4.25. When I do the first three terms and I stick in the 18, not 1, stick the 18 in, I get 4.242188. And if I go out all four terms to the third degree and I stick in an 18, you're having an 18 minus 16 is 2, 2 cubed is 8, over 4, oh, what a mess, 4.24267. And then I'm just going to write the errors down so you can see them, because everybody can take square root of 18 and subtract these numbers. So they say, and I'm going to write it again, not in scientific notation, so you can see what's happening. And then this one is going to be 0.00736, 0.000453, and then, the last one, 0.0000351. This one goes with this guy. All right, so as you see, out three terms, and look how tiny the error is.